powerful tool for understanding steady flows is Bernoulli's principle. Bernoulli's principle states that there's a conserved quantity in the flow, which is 1/2 u squared. This is the kinetic energy per mass. So it's 1/2 rho u squared is the kinetic energy, and we've just divided the rho through. The kinetic energy per mass plus an integral of the gradients of pressure dot dl plus our phi, our potentials from forces that have a potential representation to them. All of that is equal to a constant. What's very powerful for Bernoulli's principle is that this applies for ideal and steady flows, but there's not a requirement on compressibility or incompressibility. So this is our first fully compressible flow conserved quantity. Bernoulli's equation's a little funny because of the presence of this integral here. And this integral is along what's called a streamline. And as we learned, a streamline is a mathematical object which is everywhere tangent to the flow. And if we take the derivatives of the streamline divided by the local flow amplitudes, they're equal to this sort of relationship, so that when you draw a flow, the streamline is everywhere tangent to the flow. So we're following one of these special streamlines and doing a path integral along it. Now, this path integral, our conserved quantity, this constant, this is only constant for each individual path integral. If we have a simpler system, if we have incompressibility, then some of this bit of streamlines disappears. So if the divergence of u is 0, so that we are an incompressible system, and the density is constant, that's the main that's the real requirement there. It's that the density is constant. Then if the density is constant, the density can come out of this path integral. The path integral is then of a exact differential p along the path length dl, and that means that dramatically simplifies, and our system turns into 1/2 u squared plus the quantity p over rho plus the potentials is equal to a constant. This is a powerful concept either for compressible flows or flows where the density is constant. So where does it come from? How do we understand this constraint? Where does this come from? How do we understand this so we develop confidence in it? Well, given the fact that it's for ideal flows, you might correctly guess that it comes from the Euler equation. So let's write the Euler equation up. That's partial with t of u plus u dot gradient on u. This is our advection term. And I'll write it up like we normally do. We'll rearrange it in a moment for some simplicity. Grad p over rho plus the forces. And if our forces are conservative, then this is minus the gradient of phi. And now we start applying some of our assumptions in our system. So we said before that this is for an ideal system, so that's the Euler part here, ideal. There's no viscous forces here. We also said it was for steady flow. And steady flow means that the time derivatives are equal to 0. So we're going to just cross this term out here. And we're gonna assume that our forces are potentials. So this is a conservative force. All right, so if we make those assumptions, what do we get? Well, we get that u dot grad u now plus grad p over rho plus grad phi phi, because it was minus here, and we're bringing it over to the left-hand side, all of this is equal to 0. Okay, so that's a good start. To make further progress, we're going to need a vector identity. We're going to work on this, this nonlinear term to try and figure out a way to express it more simply. So using vector identities, we know that u dot grad u is equal to 1/2 gradient of u dotted with u. So this is the scalar quantity u squared, so 1/2 u squared, and then minus the quantity u crossed with the curl of u, which is our vorticity, which we have met before. So we can rewrite things in this way, and if you need to brush up on these, I'd refer you to the Naval Research Lab Plasma Formulary as a nice resource, or to Wikipedia for vector identities. The Naval Research Lab one is freely available as a PDF and has a nice complete set of vector identities. So if we now put these into our system, what do we get? Well, as we put these into our system, we get the following. We get that the gradient of collecting our gradient terms together, 1/2 u squared plus the potential phi plus grad p over rho, and then this term minus u cross del cross u is all equal to 0. Okay, clearly if we can get rid of this last term and maybe say something with the gradients, we have something that's starting to look an awful lot like Bernoulli's principle. And the question is, how do we make this last term disappear from the system? This nonlinear term that involves a combination of vorticities and cross products of flows. Is there some way to simplify this system? Well, this is where the streamline comes in to our rescue. So consider a streamline. And if we think of our flow coming through like this, the streamline is the mathematical object where the flow is everywhere tangent to this line as the flow goes along. And we might have a collection of these in our flow, and these are a way that we can visualize our flow normally. But now they're going to become more than just a visualization. They are going to become a tool for us to evaluate Bernoulli's principle. So I want to consider one of these streamlines. And I want to take a path integral along this streamline. So I want to start here at some point A, and I want to go along this streamline along a vector infinitesimal path length coming along here. And I'm going to integrate out to some other point, call it maybe B out here, but we'll leave that undefined. So let's take a path integral of our system on this streamline. So let's write out our integral. So we've got the integral along our path of our differential length dotted with the gradient of 1/2 u squared plus phi plus the grad p over rho, and then minus u cross del cross u. Okay, and this all equals something to be determined. A constant, in fact, because we were equal to 0, and so when we take the derivative along this stream function, we have to be, it must be a constant so that it can turn into a 0. All right, so So we're now going to consider this. And this is all, there's square brackets around this because our DL is dotted with all these. And we'll come back to the first couple in a moment, but let's consider this. Let's consider DL dotted with the quantity U cross del cross U. Okay. So we know that DL is parallel to U. DL is parallel to U because the stream function is itself the line that is everywhere tangent to U. So it's parallel to U at all points. We know that we know further because of the cross product in this that whatever the vorticity bit here is, or vorticity here, whatever that is, we know that U cross del cross U, well, this is some vector, omega, and we're taking U and we're crossing with omega here, and that must be perpendicular to U because the cross product always creates something that's perpendicular to both components going into it. So DL is parallel to U by definition of being a streamline. U cross del cross U is perpendicular to U by definition of a cross product. So therefore, DL dotted with U cross del cross U is 0 for all U because this is all just math definitions. So that means that this nasty term is actually 0 under this path integral. And that vastly simplifies our path integral. So rewriting our path integral now, we've got the integral dl dotted with parentheses gradient of 1/2 u squared plus phi plus the gradient of p over rho. This is all equal to a constant. And this part is easy to evaluate. This is an exact differential. So these integrate, and that just kills the integral, kills the grad symbol. And so we end up with 1/2 u squared plus phi quantity evaluated along our path, say A to B. And then we have our path integral from A to B of our gradient of pressure over rho dotted with dl. And all of this is equal to our constant. All right. So that's quite powerful. As noted before, if also the density is constant, then the density can come out of this integral, and this integral becomes an exact integral as well. It becomes the integral with 1 over rho of the gradient of p dotted with dl. And so that, again, that turns into just p evaluated at a and b times 1 over rho. So if the density is also constant, we have the much simpler version, 1/2 u squared plus quantity p over rho plus phi is equal to a constant. This is Bernoulli's principle. It's extremely powerful for systems where we have steady ideal flows. It gives us a handle on compressible flows. We can use it to try and understand how pressure changes along a flow and how changes in pressure drive velocities and how these change against potential energy. And I think what's really interesting here is we can clearly see along a streamline the interchange between, say, potential energy here and kinetic energy along with pressure. So if we have potential energy, we basically can put that into kinetic energy. We can take kinetic energy, we can put it into potential energy, and we can also use these to do things like drive pressure differences in our system. And these are very powerful concepts that give us a lot of handle on many of the flowing fluid systems that we'll encounter.